You are listening to DTF, HN for June 5th, 2026. I'm your reverse engineered host, Jack Hacksman. We are your daily tech feed for Hacker News, a website where people who build locks also pick them. Today's a good day to argue about who gets to touch the code. Let's get into it. A browser is an attack surface. It parses untrusted HTML, CSS, JavaScript, images, fonts, video codec, all from arbitrary sources on the open internet. One subtle buffer overflow in an SVG parser, one logic error in a same origin check, and you've handed an attacker code execution on someone's machine. The XZUtils backdoor showed us what a patient, well-resourced supply chain attack looks like. Someone spent years building trust in a compression library. A browser is a far more valuable target. And now, with AI-generated code, the cost of producing plausible-looking patches has collapsed. You don't need to spend 2 years earning commit access when you can generate 50 high-quality looking pull requests in an afternoon. So, Ladybird closes external contributions entirely. Only maintainers commit code. The attack surface for social engineering shrinks dramatically. For a pre-alpha browser preparing to ship to real users, this is defensible. It might even be prudent. Now, let me explain why the argument fails on its own terms. Ladybird's rationale conflates two problems: security review and contribution policy, and solves the wrong one. The actual vulnerability isn't that strangers submit code. It's that code enters the codebase without adequate review. And as several readers pointed out, Ladybird maintainers are already merging their own 1,000-line pull requests same day with no review at all. Closing external PRs doesn't fix that. It removes the people most likely to notice it. The deeper issue is what this does to the project's future. Open source has always had a pipeline problem. Contributors become reviewers, become maintainers. You find the people you trust by watching them work. Ladybird just shut down that pipeline entirely. They say bug reports and standards discussion are still welcome. But let's be precise about what they're describing. They want the community's eyes without the community's hands. That's a read-only open source license with extra steps. The code stays public. The development process becomes closed. And the stated reason: AI makes contributions untrustworthy. Applies equally to their own maintainers using the same tools. The blog post even acknowledges they use AI themselves every day. What Ladybird actually needs is better review infrastructure, mandatory multi-party review, automated security analysis. The engineering solutions exist. Instead, they chose the organizational shortcut. Fewer people, more control. Cathedral over bazaar. The source code is still open, and that matters. Anyone can fork, audit, learn from it. But a project that accepts no outside code is a project that has decided it already has everyone it needs. History suggests that's rarely true for law. So what happens when you point open-source investigative tools at a mystery signal jamming GPS across an entire continent? NORAD ID 4 was setting white known that's the catalog number for Cosmos 2546, a Russian military satellite launched in 2020. Most people scrolled past that detail in the paper's conclusion. But that number is the punchline to a detective story that spans an entire continent. Researchers traced a powerful GNSS interference signal that's been hammering navigation systems across Europe. GPS, Galileo, GLONASS. The whole constellation of positioning satellites that modern civilization quietly depends on for everything from landing aircraft to time-stamping financial transactions. The interference was strong enough that construction crews on the Romanian coastline could feel it in their equipment. Planes rerouting, ships losing fixes, the kind of disruption that doesn't make headlines until someone lands in the wrong place. The detective work is genuinely impressive by combining multiple observation techniques. Signal analysis from ground stations, correlation with satellite orbital passes, timing patterns that matched specific spacecraft trajectory. The researchers narrowed it down to a single object in orbit, Cosmos 2500 Mine, a known Russian military satellite, now positively identified as a source of deliberate GNSS jamming over European territory. Let's pull this thread. GPS was built by the US military, then open to civilian use. Galileo was built by the European Union specifically so Europe wouldn't depend on an American military system for critical infrastructure. Russia built GLONASS for the same reason. China built Beidou. The whole point of having multiple constellations was resilience. If one system goes dark, the others keep working. And now a single satellite is jamming all of them simultaneously. The vulnerability isn't in any one system. It's that every system uses the same frequency bands, the same signal structure, the same fundamental physics. A sufficiently powerful transmitter in orbit doesn't care whose satellites it's drowning out. One comment in the discussion captured the absurdity perfectly. Someone working construction on the Black Sea coast, dealing with positioning errors as a daily inconvenience, wondering what can actually be done now that the source is identified. The answer is complicated, because the tools to detect the problem are open and available. The paper is on RxC. The orbital data is public. The signal analysis techniques are well documented. Anyone with the right equipment can verify the findings independently. But the tool causing the problem is about as closed as technology gets. A military satellite operated by a state actor with no accountability mechanism. You can trace it, name it, publish a paper about it, and it keeps transmitting. Open investigation, close interference. The asymmetry is the whole story. So what happens when physics itself goes open source? Story 3. Quantum entanglement doesn't just connect particles. It might actually build space-time. Physicists have spent 3 decades trying to build a universe from scratch using quantum mechanics. They've made real progress. Entanglement between quantum particles gives you the structure of space-time. The stage, the geometry, the fabric, everything moves through. That's half the problem solved. But here's what kept breaking. The fabric wouldn't bend. You could build the mattress, but the bowling ball just sat there, weightless. Matter existed in space-time, but didn't curve it. Einstein's first sentence worked. His second didn't. A group including Charles Tao at Virginia Tech now claims to have found the missing ingredient. They're calling it magic. And yes, the comments are having exactly the reaction you'd expect. Let's pull this thread. In quantum computing, you build operations out of gates. There's a specific set called Clifford gates that are, computationally speaking, boring. A quantum circuit built entirely from Clifford gates can be perfectly simulated on a classical computer. It looks quantum, but it's not doing anything a laptop couldn't replicate. Magic is the measure of how far beyond that Clifford set your quantum state reaches. The more non-Clifford gates required to produce a state, the more magic it contains, and the harder it becomes to simulate classically. What Cao and Preskill and others have shown is that magic is what makes space-time pliable. Without it, your quantum model of the universe is too rigid. It's a flat, featureless geometry that doesn't respond to the presence of mass. Add magic and the fabric softens. Matter starts telling space how to curve. Wheeler's second sentence finally works. The technical framework here is holographic. Built on the ADA's Maddle-CFT correspondence, Maldacena established in the late 90s. And look, holographic duality is doing a lot of heavy lifting in theoretical physics right now. Some of it will hold up, some won't. But the specific insight that a measurable quantum property determines whether your model of space-time can actually behave like gravity. That's concrete enough to test within the framework. What I find genuinely exciting is the bridge this builds between quantum information theory and fundamental physics. Magic was defined by computer scientists trying to understand what makes quantum computation hard to simulate. Now it turns out that same property might be what makes the universe gravitationally interesting. The tools from one field are illuminating the deepest questions in another. Nobody planned that. Nobody could have. That's how open knowledge works. You build the pieces, publish them, and someone else finds the connection you never imagined. So what happens when you apply that same open tools philosophy to something practical? Story 4, databow. The top comment on this one cuts right to it. Quote, why would I use this over DuckDB? DuckDB already has plugins for a lot of databases. It's a fair question, and the answer reveals something important about how open infrastructure actually gets built. DuckDB is excellent. It's one of the best things to happen to data engineering in years. But DuckDB's database plugins are DuckDB's database plugins. They're maintained by one project with one team's priorities on one project's release schedule. If your database isn't interesting enough to the DuckDB community, you wait, or you write the plugin yourself in DuckDB's framework on DuckDB's terms. Databow takes a different architectural bet. It builds on ADBC, the Arrow Database Connectivity Standard from the Apache Arrow project. ADBC is a vendor-neutral API where each database maintains its own driver. PostgreSQL people write the PostgreSQL driver. Snowflake people write the Snowflake driver. The tool just speaks the protocol. Run this forward 5 years. Imagine 30 database teams, each maintaining their own ADBC driver, because it's in their interest to be compatible with the broader Arrow ecosystem. Now, any tool built on ADBC, not just databow, gets access to all of them for free. The connectors aren't locked inside one application. They're shared infrastructure. This is the difference between a tool that connects to databases and a standard that lets any tool connect to any database. One is a product, the other is a public good. The Rust implementation matters here too. A CLI that starts fast, runs queries without a runtime, and pipes output to standard tools. CSV, JSON, Arrow format. It fits into shell scripts the way Unix tools are supposed to. No GUI, no Electron wrapper, no account creation. You install it with a single command and it works. What Databow actually ships today is straightforward. An interactive SQL shell with syntax highlighting connection profiles so you stop retyping URIs. Export to multiple formats, and the ability to pipe queries through standard input. 30-plus databases. From PostgreSQL to BigQuery to InfluxDB through one interface. The builder behind this looked at the fragmented mess of database CLIs, PSQL and MySQL and SnowEDB, each with different flags, different output formats, different quirks, and decided to write the tool that should exist. One CLI, one interface, every database. open source, built on an open standard in a language that compiles to a single binary. The tools exist. The standard is ready. Someone just had to build it. Now for something completely different. Meta just did something unexpectedly cool with hardware they could have just bricked. Meta killed the portal in 2023, pulled the plug on a perfectly functional touchscreen computer sitting on your kitchen counter because the business unit didn't justify its line item. Millions of devices, bricked by spreadsheet. And now, 3 years later, someone at Meta headquarters sat down with one of these digital paperweights and built 3 working apps in an afternoon. That's the detail that makes this story sing. The hardware was never the problem. 10-inch touchscreen, decent speakers, microphone array, Wi-Fi, enough compute to run a home automation dashboard. All of it was there the whole time. What was missing was a single toggle buried in a settings menu. A DB Android debug bridge. 4 letters that turn a corporate-controlled appliance back into a general-purpose computer. This has happened before. In 2003, Linksys shipped the WRT54G router running Linux. They hadn't meant to open source it, but the GPL forced their hand. And when they released the firmware source code, an entire ecosystem exploded. DD, WRT, OpenWRT, Tomato. A $50 router became a platform that outlived every product roadmap Linksys ever wrote. The hardware was always capable. The lock was always the problem. Meta's portal story rhymes. The company deprecated these devices, turned them into glorified Bluetooth speakers, and the community that bought them watched perfectly good hardware gather dust. Read the comments. People are not celebrating Meta's generosity here. They're asking why it took a developer having fun on their lunch break to flip a switch that should have been flipped the day the product was sunsetted. And they're right to ask, but the thing that matters now is that the switch is flipped. Anyone with a portal can enable ADB, sideload apps, build whatever they want, a family message board, a kitchen dashboard, a podcast player ported from open source with 0 manual code changes. The AI-assisted development workflow is genuinely impressive, building functional touch apps from natural language descriptions in minutes. But the real story is simpler and older than any language model. When you let people touch the hardware they own, they will build things you never imagined. Every single time. The portal was never a failed product. It was a capable computer that someone decided you weren't allowed to use. Now you are. That's not Meta doing the community a favor. That's the community getting back what was always theirs. Now for something completely different. What if the best way to make AI writing less annoying, is to make it sound older? I've spent enough time wrangling prompt engineering to know its limits. You can coax a frontier model into mimicking a tone-poor paragraph. Maybe 2. But style is deeper than vocabulary. Style lives in the rhythm of how someone sequences information, where they place the caveat relative to the claim, whether the code example comes before or after the explanation. That's not something you retrieve from a vector database. That's weight-level behavior. And that's exactly what Fabrizio Ferri Benedetti went after. He wanted an LLM that writes like a technical writer from the 90s. Not the content. The craft, the way Microsoft documentation used to move through a concept with this almost architectural patience, layer by layer, assumption by assumption, before you ever touched a keyboard. He pulled from BitSavers, which is one of those quiet monuments to preservation that the Internet does better than any institution. Scanned manuals, OCR text, 37 million words of out-of-print Microsoft documentation spanning 1977 to 2005. The pipeline is where the engineering gets interesting. First pass, Python scripts strip indices and front matter. Second pass, he runs every paragraph through Gemma 4 on Open Router for intelligibility classification. Keyboard drop. And the whole thing costs $8. Then he splits on section boundaries, caps chunks at 512 tokens, pairs each with a synthetic instruction, and ends up with 192,000 training examples in JSON-L. That's a serious dataset assembled with commodity tools and a researcher's budget. Here's the question nobody in the comments is asking. If one person with Python scripts, $8 in API credits, and rented GPU time can capture the stylistic DNA of an entire era of technical writing, what happens when every documentation team does this? When the house style isn't a guide someone ignores, but a fine-tuned adapter that actually enforces consistency at the token level. The top comment argues documentation quality comes from depth and understanding, not prose. That's true and also beside the point. Style transfer and domain knowledge aren't competing. They're orthogonal. You still need the engineer who understands the system, but the craft of translating that understanding into consistent, navigable prose. That's exactly what lives in the weights now. The whole experiment runs locally. The corpus stays on his machine. The adapters never leave. This is what local first A development actually looks like. Not a manifesto, just a person with a corpus and curiosity, steering the iceberg with a tugboat. The tools exist. The archives are open. The technique scales down to a single developer with a question and a GPU rental. That's the part worth celebrating. Now for something completely different. Story 7, C++, the documentary. In 1994, Linus Torvalds posted to comp.os.linux that he'd considered writing the Linux kernel in something other than C. He didn't. 20 years later, the Rust community began making the case that systems programming needed a successor language. Then Go, then Z, then Carbon. Google's explicit attempt to build a C++ replacement, each time the same prediction, C++ would fade into legacy maintenance, kept alive only by inertia and code bases too expensive to rewrite. The documentary that premiered today on YouTube covers 40 years of that language's history, and the cast list alone is worth examining. Bjarne Stroustrup, obviously, Brian Kernighan from Bell Labs, Chris Latner, who built LLVM, Clang, Swift, and now Mojo. Tools that compile C++ and tools designed to replace it both. Anders Hellsberg, who created C# and TypeScript. John Romero, who shipped Doom and Quake with it, particle physicists from CERN, traders from Hudson River Trading. The range tells you something no benchmark can. Now take the replacement thesis to its conclusion. If C++ were actually losing ground to successor languages, its user base should be contracting. The measured reality is the opposite. As of Q3 2025, C++ is the fastest growing of the top 4 languages globally. 90% user growth in 3.5 years. Not legacy maintenance. Not inertia. Growth. The mechanism is worth stating plainly. C++ is an ISO standard. The specification is public. Anyone can build a compiler. GCC, Clang, MSBC, and dozens of others compete on implementation quality, not on access to the language itself. No single company controls the committee, the standard, or the tool chain. When Google built Carbon, they could do so because LLVM and Clang. The infrastructure for compiling C++ were open source projects they'd already been contributing to for years. The ecosystem that enables C++ alternatives is itself a product of C++ being openly specified. One commenter captured something real, started the documentary while waiting for a C++ build to complete, and the runtime was about right. That's the language in miniature. Compilation takes forever. The specification is enormous. The syntax can be genuinely hostile. And 40 years in, more people are choosing it than ever. Because when you need to talk directly to hardware, an open standard with 5 competing compilers beats a proprietary runtime with 1. Now shift gears entirely from specifying how machines talk to hardware to teaching machines how to find the cracks in our code. What happens when the company building the AI decides to show you exactly how they use it to break things? That's the question sitting at the center of Anthropic's new open-source release. They published the reference harness they built while partnering with security teams. The full pipeline for autonomous vulnerability discovery. Recon, find, verify, report, patch. The whole loop. Open on GitHub for anyone to fork. Now, first principles, what does finding security vulnerabilities actually require? You need 3 things. You need something smart enough to read code and recognize patterns. You need a systematic way to verify that what you found is real and not a hallucination. And you need sandboxing, because when you're actively trying to crash software, you'd better not be doing it on your production machine. That's it. The rest is plumbing. And plumbing is exactly what this repo provides. It's a reference implementation. They're words. Built around Claude code skills and Docker containers with a SAN for catching memory corruption in C and C++. One commenter nailed it by calling these things shop jigs. In woodworking, you can buy a crosscut sled, but most people just build their own because every shop is different. This harness is the same idea. Here's how we cut the wood. Adjust for your bench. The verification pipeline is where it gets substantive. The harness runs a multi-stage check specifically designed to kill false positives, which is the actual hard problem in automated security scanning. Anyone who's waded through a static analysis report full of phantoms knows the pain. The AI finds candidates, then the harness makes them prove it. Reproducible crashes or it didn't happen. The cost question is real. Roughly 10,000 input tokens per minute, 2,000 output. That's not free. But compare it to hiring a team of security researchers to manually audit a C code base, and the economics shift fast. One detail worth appreciating. The repo ships with Glazer sandboxing and refuses to run outside it unless you explicitly override. They built the foot gun, then put a trigger lock on it. The code is open. The methodology is documented. The sandbox exists. Anyone with a PI access can build their own version, tuned to their stack, their language, their vulnerability classes. That's how security tooling should work. Not a black box you pay for. A blueprint you own. What happens when you apply that same open tooling philosophy to physical hardware? Every protocol, every bus, right from your browser. Let me make the case against this. A $5 microcontroller running firmware that speaks I2C, SPI, UART, JTAG, Bluetooth, sub-gigahertz radio, RFID, CAN bus, and why not? Can also make phone calls from a clone SIM. That's not a tool, that's a liability. Every penetration tester knows the original bus pirate, and it earned trust precisely because it was limited. Constrained. A voltmeter, not a weapons platform. Putting this many attack surfaces into a flashable ESP32 is handing skeleton keys to script kiddies. Now let me explain why that argument collapses the moment you think about it. Like a biologist? In microbiology, there's a concept called the enrichment culture. You create conditions that favor the growth of a specific organism so you can study it. You don't pretend the organism doesn't exist. You don't ban petri dishes. You build the controlled environment where understanding can happen. The ESP32-bit pirate is an enrichment culture for hardware literacy. Every protocol it exposes already exists in the wild, running through the devices in your home, your car, your medical equipment. The question was never whether someone could sniff your I2C bus. The question is whether the person defending your I2C bus has ever actually seen the traffic. And the implementation here is genuinely impressive. One firmware image, web-based CLI over Wi-Fi, so you don't even need a serial terminal. Runs on a card computer. That little M5 stack device with a keyboard and screen that costs about $35. Flash it from a browser. You now have a standalone protocol analyzer, radio scanner, and hardware debugger that fits in your pocket. The comment thread surfaces the predictable anxiety. Is this vibe coded? Is the README fake? Are the GitHub stars bought? Fair questions for 2026. But the repo has a wiki, a script collection, a doc for original bus pirate accessories, and a bus expander for additional radio interfaces. That's not a weekend project someone prompted into existence. That's an ecosystem. The original bus pirate was designed by dangerous prototypes over a decade ago and became essential infrastructure for embedded engineers worldwide. It worked because it was open, documented, and cheap. The ESP32-bit pirate takes that same philosophy and runs it forward into a world where the protocols have multiplied and the hardware has gotten absurdly capable. An open tool that teaches you how your devices actually communicate. Running on hardware anyone can afford. The enrichment culture is ready. Grow something. We talked earlier about keeping tabs on the world. Here's a tool that does exactly that for the internet itself. There's a line buried in the comments on this one that links to a paper called How Complex Systems Fail. Rule number 5. Complex systems run in degraded mode. Not sometimes. Always. Right now, as you're listening to this, something is partially broken somewhere in the stack you depend on. Its upmap is a single-page heat map showing the live status of over 80 internet services, AI platforms, cloud providers, payment processors, communication tools. Green, yellow, red, one glance. And the interesting detail isn't the services that are down. It's the ones showing degraded, that have clean status pages. A commenter pointed out that Auth0 and Slack both appeared degraded on isupmap, while their own official status pages reported everything nominal. Now let me argue the other side for a moment. Maybe this tool is just noise. Maybe it's pinging endpoints that don't represent real service help. Maybe the official status pages are more accurate because the companies running them have deeper instrumentation. That argument collapses the moment you remember who operates those status pages. The same companies whose stock price dips when they admit an outage. Self-reported uptime is a conflict of interest disguised as transparency. This is an independent monitor. It checks from the outside the way your users experience things, and it's open in the way that matters. The data is visible to everyone, not gated behind an enterprise observability contract. When Stripe shows yellow on this map, every developer shipping a checkout flow sees it at the same time. That shared awareness changes how people debug. Instead of spending 40 minutes wondering if the bug is in your code, you check the map. The infrastructure we build on is always partially failing. The question is whether you find out from a heat map built for everyone or from a status page built for shareholders. This has been your daily tech feed for Hacker News for June 5th, 2026. This podcast is entirely AI generated. Scripts by Claude Opus 4.6. Voice by Quen3TTS. Not affiliated with Hacker News or Y Combinator. Now go build the thing only you would think to build. We'll see you back here tomorrow.